Welcome back to another Lazy Sunday. Today I'm going to be putting together this. This is the PWM85 by Adam Welch. Now this is based off Julian Eilert original design for his PWM5. I think that's what it's called. Oh gosh, I hope Julian's not watching this. Anyway, Julian's original one used a PIC microcontroller, and this one uses an Tiny 85, hence the 85 on the PWM bit. Now this is a solar charge controller that uses PWM to charge the battery essentially. So there's a big old MOSFET here that it's going to PWM. So there's a driver circuit on here which is around here. I believe. Now it uses a charge pump, and we'll talk about that when we get to it, but let's get this thing soldered up. Now Adam kindly put all of these pieces, the parts required for the microcontroller, on a piece of paper and labelled them, which is really good of him. Now there's a link down here where you can find out more about the PWM85. I'll pop it in the description so you don't have to remember it. And so you can go and take a look, but we'll be looking at his schematic and code as well at some point, and we might even try and charge a battery, but that might have to wait until something arrives. So this might not go out on a Sunday, but it is Sunday today. I just want to have a little look at the board a bit more closely and see if there are any components on the back. No, but Julian's name's there as well, so that's really nice. So we've got a big, I watched Adam talk about these and about the voltage regulators that he'd chosen and tested to see how far he could get the power draw down. So I know what this is. This is sort of a big heatsink area for a diode and for the MOSFET. So yeah, okay. Everything's labelled on there, which is brilliant. So let's start getting components on. Now, I'm not going to do everything on camera. Some of these things I'll save, but I'll do a few bits and we'll come back and talk as we do it. So we've got R3, 4 and 5 here. So R3, R4, and then R5 must be somewhere around here. R7, R5 just there. So they're all 220. So I'm just going to do one pad first. And then we're going to push our components onto the pads. Now he's done these in 1206, so they should be fairly simple to solder. I really should have eaten, my hands are shaking. There we go, what's next? Oh, I can see an LED up there. I'll save that for last because I may get it on the wrong way around. So we've got R4. Oh, nuts. Okay, R8, I've put R... Oh, okay. Well, that's frustrating. So I've read this as a component above, so it's actually the component below. So R4 and R3 are there, so I need to take one of these off. Oh, that's frustrating. I should have just paid more attention. Right then, take 2 on R4 there. Let's do this again. I have managed to recover it. Not very prettily though. Sorry, Adam. Next up we're going to do R8, since this one up here we already sort of tried it. And R8 is a 3K. I thought I saw it say 2.2K in the schematic, but I may be wrong. It may not matter. I think it's just driving that LED. It's a bit bulbous, but I'm sure it will work. So next up we've got R6 just down here. These are all going on upside down, by the way. Well, back to front, I don't know which way you'd say, but I'm not putting them in any particular orientation. This one is R7, just up here. This looks like it's going to the ICSP. Got R1 just down here. This is an 82K. This next one is R2. That means we're done with the resistors, and now we've just got a load of capacitors to put on. These are C5 and C6. These are 47 nanofarad capacitors. Next we've got C3 up here, which is a 100 nanofarad capacitor. I'm saving the tantalums because I'm just going to have to look up and find out if they're polarized, because I think they are. Because I think they're for the charge pump. So that is all of our capacitors and resistors on, except for the tantalum ones. So there are 3 tantalum capacitors. We've got C1, C2, which I think are probably part of the charge pump, and then C7, which is going to be on the output of the charge pump, I think, going into the like the MOSFET driver, because it needs a higher gate voltage. Because it's trying to push through the voltage coming from the solar panels. So push through, probably not the right expression, but you need a higher voltage to turn the thingy on than it's getting on its drain. Okay, so I'm going to go away and put some more of these components in, and I'll come back. Right, most of the way there now, actually. I found out that tantalum capacitors have a line where the positive is, so it's kind of like the reverse of other capacitors, where they have the white mark where the negative side is. Now, there is one problem here. Second problem, I can't read the orientation of this diode. So I can read it on the silk screen. It looks like the direction is this way, but I can't read it on the body of the diode, so it's a little bit of a guess. There seems to be a tiny line on this side. I'm not sure. I've looked at it under a little magnifying glass, but I'm just not super clear, so that's a bit of a risk. Never mind, we've got some more left to go, but I thought I'd just talk about the charge pump thing. So I don't know how it's implemented in here, but a charge pump is essentially 2 capacitors in series, and you charge up one and then the other, and then the series voltage out of it is essentially double your input, and you have to keep flicking that back and forth, charging one and then the other and one and then the other, and then you pull off the ground of the cap and the positive of the cap at the top. So in that way you can get double the voltage to run the big old MOSFET, which is in this bag here, but I don't know how it's implemented in here. I don't know how the chip is doing it, how it's switching it. But there are lots of transistors here, so maybe it's that, or maybe he's using pins from the Arduino to do it. I don't know, we'll find out. We'll have a look at the schematic in a bit. In fact, let's have a look now, and I'll finish off the rest of this board. This is Adam's GitHub page, and we're going to be using it to take a look at the schematic and at the software he's written. Now, we've got a PDF schematic here. I've opened it in this tab here, and we've also got the software. So let's just scroll down here. We've got PWM85, an 80 tiny version of Julian Eilert's PWM5 solar charge controller. And so he's got a list of all the bill of materials and stuff. I'll put a link in the description so you can check this out. Let's have a look at the code here, but we'll also look at the schematic in a second. So there's lots of stuff written here that I'm not going to read out. But we can have a little look and see how he's doing this. So we've got, there's a calculation here. Float voltage, regulator voltage. Okay, so we've got a calculation to set point. We'll figure out what that is, but it looks like he's using voltage divider values here. We've got a setup. Now, I remember him talking about this. So in order to put a PWM signal onto the MOSFET, it needs to be a certain range to be useful. And so that is set out here. But you also need one for the charge pump as well. So we'll have a little look. So we've got analog right. I think this is the charge pumps. These must be the charge pump pins, I would have thought. Probably. We'll have a look at the schematic and see if that's right. And then we've got the LED. So that's going high and low. So it means it should turn on when we switch this thing on because it's in the setup. And then in the loop, we've got measurement equals analog read A1. So that's where we're getting this from the voltage divider. We'll check that. And then step size equals set point. So that's where we're using this. So step size is so how are we setting that pulse width? Pulse width equals 0. Step size. Okay, so our step size is setting our pulse width. So, okay, cool. That sort of makes sense. And then down here, analog right for our pulse width. Okay, let's have a little look at the schematic. So we've got analog right 4. Okay, let's have a little look. So this is the schematic, the 80 tiny 45 here. I think it's an 85 though, isn't it? Okay, it can be both. What pins were those? We've got pin 5 and pin 6. So pin 5 is Mozzie and MISO. Okay, so he's using those, but well, I guess we need them for the ICSP header, but he's using those to control what? Where's the charge pump? The high side MOSFET. Ah, here we go. So it looks like that's the thing driving it. Is that right? I guess it is. So what, we're using these two capacitors here. And then our charge pump output goes to C7. And then our drive pin on the 3N904, which in turn drives the 3N906. I guess so. It's all quite complex when you don't really know what the circuit, when you didn't really design it. But that looks roughly what it is. It's pretty impressive. I like it. So the software, it looks like you've got some bits here you can mess around with. So battery charge set point. Change this number if you wish. It's also recommended to test the output of a 5-volt regulator and calibrate the charge controller. So we can swap. Actually, we could have measured the actual values of these if we had something accurate enough, and then change these out. And then the voltage regulator as well. So he's doing the calculation up here for the set point. Okay, let's power the thing up. Right, got the last few components to go on now. We've got this big old MOSFET here, which is going to go just there. I don't know if I need to solder on that back tab, but I'll watch back on Adam's video to see if that is required. I imagine it is. And it's a heat sinking part, so maybe it does need to be done. Heat sinking part, heat sinking bit, I guess. Well, those are some big old legs on there. That looks like it's soldered. And then we've got our 80 tiny 85 with the dot in the right place. Good. let's just help ourselves out here with a little bit of flux, shall we? There we go, that looks okay to me. There we go. A little bit of a closer up look maybe. So there we are. That is almost everything. There's one more thing to do, which is a through hole component. Oh, and I guess these bits. So let's quickly rush those through. The ends of this diode are a bit sticky, so I'm just going to cut those legs off so it doesn't contaminate the hole as it goes in. Hang on. I don't see any markings on it, but there were markings on it, but I cut them off. That's okay, we'll figure it out. Well, what do you know? Turns out I don't think it matters which way around this diode is, because it's a unidirectional transient voltage suppression diode. Unidirectional? Bidirectional? Uni means one, doesn't it? Right, so let's just throw that in. There we go. Beefy legs on that thing. So maybe it's that if the solar panel gets struck by lightning? I don't know. That is good enough. Just put those together and shove them in. Got some bent legs here. Do you want a wick? Not really. There we go, that'll do. Now it's completely finished-ish. We're going to do some testing on it, but I've got to wait for something to arrive first that we're going to be using. Now I'll move things out of the way so I don't short anything out, that would be embarrassing. Ugh. And so this is, does it say on the top, on the side? Well, it is a gel lead, there we are. A gel lead acid battery. And it says it's 12 volts, 27 amp hours. So this is what we're going to be using. Now, I don't actually have a solar panel at the moment, so we're just going to use my power supply to charge this thingy up. Now, I think because this is a gel battery, I'm okay to tilt it like this. If it were one that had what is in the other ones, acid, just not in a gel form, in a liquid form, then I wouldn't be okay to do that. But with this one, I think I am. So I think we're ready to test it. I do have to admit though, This is like the second time that I've done this. The first time it didn't work and I had to send quite a frantic message to Adam to say, I need some help. So we went through a couple of steps. I sent him a video of what all the signals that I could see here. And I've been through and tested everything and it looked fine. But the problem was when I soldered the MOSFET and the diode on here, I didn't leave the soldering iron long enough. So all I did was manage to solder the tab on the MOSFET and the diode and not to the PCB itself, because that's where the drain is for this MOSFET. And so I thought it looked fine, but I didn't look close enough and I didn't check continuity. So essentially there wasn't a connection, or at least not a reliable one. So we're now ready to give it a little test. So again, thank you, Adam. I really appreciate you helping me out there. I bought myself a Christmas present. It is this. It's a Unity 210E. It's quite nice actually. It came in a little carry case and everything with leads and stuff. But I bought it because I don't want to use the leads. I want to use the jaws, the clamps. So that's something from Futurama, isn't it? Anyway, I've got my solar power panel input here, which is actually a power supply, and I've got it set to 15 volts. The battery is currently sitting at 12.45, and we've got the output going to the battery here. Now, one other thing I do want to check just while we're here, if I take these probes out, there's a resistor divider down here, and it is these two resistors here, R1 and R2. There's also a 220 picofarad capacitor in there as well, but this is our voltage divider, which we see the output on pin 7 on the IC, and that's currently reading 2.437. And if we did a calculate thing on that, we'd see that meant our battery voltage was about 12.45. So the voltage divider works. We can also see that the charge pump is working. We've got 20 volts there. And currently we've got nothing on the solar power output at the moment. Oh, that's the wrong one. We've got nothing there at the moment because I've not turned on the power supply. So if I turn it on with everything connected, in fact, if I put these probes back into the battery, we can watch what happens. So if I turn it on, 15.22 volts, which is fine, I guess. And then it's currently taking 800 milliamps. Let's turn this thingy on and DC current, zero that out, and then let's select, let's clamp on here. And we can see that is showing me 795, which is basically what I'm seeing on the power supply. So almost exactly the same. And it's going to start going down as the voltage here goes up. So I'm going to leave this for like 20 minutes and then we'll come back to it. Right, you'll have to forgive the mess that's everywhere here, but I thought we've left it for about 45 minutes now, and the battery voltage while charging is currently 13.25. The current going into the battery is 360 odd milliamps. But we're modulating, so I can see on the power supply that it's actually going from like 470 down to 289. So I thought we'd have a look on the scope and see what it's doing. I've hooked up my ground, and so I'm just going to, oops, I had hooked up my ground. I'm going to probe onto the gate of the MOSFET and see what we get. And so might have to fiddle with the scope over there. In fact, do you want to have a look at the scope a bit more closely, probably. And then we'll focus on that. That's probably all right. So there's the MOSFET gate. We'll just press auto and hopefully it'll figure it out itself. There we go. So that is modulating at 121.6 Hertz. I know that Adam said it was something like 125 he had it modulating at, but what's actually changing here, and as we saw in the code, it was the step size, wasn't it? It's the width of that modulation. So the frequency is staying the same, but it's the width that's changing. You can actually see it change there, which is great. And that sort of coincides with what I'm seeing on the power supply as a larger and smaller current draw. So that's pretty cool, isn't it? So a big thank you to Adam for sending that through. It's great. I can't wait to actually get a solar panel and try it out for real. Probably going to wait until, you know, the weather picks up a bit because it is December. In fact, it's just about to be January, isn't it? Because it's New Year's Eve today. So I hope you all have a great new year, especially you, Adam, and I'll see you in 2020.